Hello APC Mechanics students in Unit 6 Oscillations, Class 4, 6.1 Simple Harmonic Motion Horizontal Oscillator, Part 4. Now, Section 1 Differential Equation of Horizontal Oscillator, Energetic Approach. Now, previously we have determined the differential equation of a horizontal oscillator using a big law, which is Newton's second law. Now, a good question to put forward is that, since we're talking about big laws or big ideas, is it possible that we can determine the differential equation of horizontal oscillator via conservation of energy, since also we don't have friction? Then let's see. Previously we have determined the differential equation of a horizontal oscillator using Newton's second law. The aim of this section is to determine again the differential equation using energetic approach from the conservation of mechanical energy. For that, consider a horizontal oscillator formed of a block of mass m and a spring of stiffness k. The block is connected to the spring and the other free end of the spring is attached to a support, thus forming the horizontal oscillator. Consider a point along the motion of the oscillator between the equilibrium position and amplitude, and that is the position x. Let's assume the spring is ideal, governed by Hooke's law. Assume that friction between the surface and the block is neglected. The beauty about this approach is that no diagrams or directions are needed to solve for the problem. So if you remember that directions in Newton's second law are important, because when we wrote the vector equation, then we obtained the following equality, which is given by minus kx is given by ma, and we stressed on the fact that this minus sign is not related much to direction. However, this is due to the restoring force, which means that in Newton's second law we need to take into consideration direction signs related to the nature of the force, and whenever we add friction, also we need to pay attention that the friction should be positive and not negative. Now, in the energetic approach, no need to worry about this stuff. For that, take the PE level to be the horizontal passing through the center of mass of the block, as we have done here. Now, the mechanical energy of the oscillator is given by kinetic plus gravitational plus elastic potential energy. We can directly eliminate the gravitational because the center of mass of the block passes through the PE level, and we're left with half mv square plus half kx square. Now, since there are no frictional forces, then the mechanical energy of this oscillator is conserved, which means it's constant in value. Now, what is the value of this constant? We don't care and we don't know. Now we're gonna derive both sides with respect to time. So as you can see here, we have applied the time derivative operator. And in this case, that would be 0 because a constant with respect to derivative, with respect to time, that would be 0. And here we have applied the distributivity property over the addition. Now we're interested in deriving half mv square, knowing that the only variable is the speed, because as the block oscillates, the speed is variable. Then half m is a constant, can be dragged out. Now, what is the derivative of v square? Notice that this is a v and not t, so v is a function of time. Then we need to apply the chain rule. We drop down the power, so that would be half m 2. We reduce the power by 1 and we multiply by the derivative of the function, which is v prime. And that would be mv prime, because 2 cancels with the half. It is important to remember that d by dt of v square is 2v prime. This is an important result. Or simply you should remember that the derivative of the kinetic energy is mv prime. And for the elastic potential energy, half k is a constant, can be dragged out. Now we're deriving x square. Now x is not t, it's a function of t. For that we need to apply the chain rule again, and that would be 2xx prime. And we obtain the following after we have derived this and we have derived that. Now also you can notice that all of these variables can be unified for x, because we are searching for the differential equation that governs the motion of the block in terms of x. Now v is x prime, and v prime, which is the acceleration, basically is x double prime. Then in this case, we have the following: mx prime x double prime plus kx x prime is equal to 0, and we can factor out x prime. Moreover, we can simplify, or we can ignore the fact that x prime, because x prime is different than 0. So here what I'm trying to say that if this is equal to 0, which means this is equal to 0, or this is equal to 0, but this happens to be different than 0. Why? Because this is speed, and the oscillator, except for the amplitudes, the speed is different than 0. So in general, the speed is different than 0. For that, we can ignore x prime, and which means that mx double prime plus kx is equal to 0. And if we linearize the double derivative and we divide by m, we would obtain the same differential equation, which is given by, so here all the time I was using prime as the derivative. If we convert it to the dot notation, we would obtain the same differential equation that we have obtained previously. Remarks: in the presence of frictional forces, the differential equation can be obtained by using the variation of mechanical energy or the work energy theorem, for example. This method only works whenever there is no friction. In the case of friction, we need to use either the variation of mechanical energy or the work energy theorem. Now, section 2, energy interchange of horizontal oscillator. Consider the same oscillator that have been discussed so far, characterized by mass m and stiffness k, and neglect frictional forces. The oscillator possesses two types of energies, kinetic and elastic potential energy. And here for sure we are talking about ideal spring, because the elastic potential energy that we're using is given by half kx square. The mechanical energy of the system is given by half mv square plus half kx square. Then there is a continuous conversion from kinetic to potential and from potential to kinetic as it's oscillate. Let me explain more. So if the kinetic energy increases, so here what I'm trying to say, this quantity is constant. Now, this is constant, it doesn't mean that this is constant and this is constant. The sum of both are constant, knowing that this is a variable quantity and this is a variable quantity. So here what do we deduce? If the kinetic energy increases, the elastic potential energy decreases. So if K increases, potential energy decreases, and if potential energy increases, kinetic energy decreases. Kinetic energy is half mv squared, it's about speed. Then you can think about that whenever we are talking about kinetic energy, we're talking about speed. Elastic potential energy is about position, so you can think about it whenever we're talking about elastic potential energy, we're talking about position. Let's recall the following. The position is maximum when the speed is 0, and the speed is maximum when the position is 0. So what can we deduce from all of that? Now consider the oscillator at different, so here I have labeled for you the P level, the amplitudes, and the equilibrium position. At a particular point, neither to be the equilibrium nor the amplitude, the energy, the mechanical energy, is given by half mv square plus half kx square. Now considering the amplitude, which is on the right, the position is maximum, the speed momentarily is 0 because the block is about to change its direction. The elastic potential energy is maximum, the kinetic is 0, and the mechanical energy of the oscillator, instead of writing it as half mv square plus half kx square, we can simply represent it by half kxm square. Now consider also the other amplitude, although this position with respect to the origin is negative, but okay, so here if I want to be precise, I should place a minus sign, not like that. Now the speed is 0, the elastic potential energy, again, it's maximum, kinetic energy is 0, and the energy, so here let me also state why the speed is 0, because at this particular point the block will change direction and start oscillate backward to the right. And the mechanical energy of the oscillator is given by half kxm square, which is purely elastic. Now at the equilibrium position, the position happens momentarily to be 0, the speed is at its maximum, the elastic potential energy, because it's related to position, that would be 0, the kinetic energy, which is related to the speed, that would be maximum, which is half mv square m, and the mechanical energy in this case is given by half mv square m. So you notice that the mechanical energy of the oscillator has three different forms. It's given by half mv square plus half kx square, or can be expressed as half kxm square, or even as half mv square. All of these three quantities are equal to each other. A good question also to put forward, as there is a continuous interchange between K and US. Where does K and US equate? So here, if you want to put numbers, let's suppose that the mechanical energy is 6 joules. Now, if you do a diagram, you will notice, or you can think about it in this way. This might be 0, this might be 6, this might be 1, this might be 5, 2, 4, 3, 3, 4, 2, 5, 1, 6, 0, and all of these number has the unit of joules. So when does both, so let me say, as there is a continuous interchange of two forms of energy, kinetic and potential, is there a point, or what is the point in which both energies equate? We're talking about the position. At what position? Is it half the amplitude? So does both energies are both energies equal at half the amplitude? Because you know that whenever we're going from equilibrium to the amplitude, one of them increase, which is basically the elastic, and the kinetic energy decreases. So do they equate at this point? Let's see. This means that the elastic potential energy is equal to the half the mechanical energy. Now we're trying to find where does these 2 points equate. So if both of them are equal, this means that the elastic potential energy should be equal to the total mechanical energy divided by 2. But we know that the mechanical energy has 3 different forms given by half mv square plus half kx square, which is also equal to half kxm square, which is also equal to half mv square m. So if both energies equate, which means each one solely is equal to the half of the total mechanical energy, which is the big boss in this case. Now E can be replaced by one of these 3. I will replace it by this one. So we can say that half kx square can be equal to half multiplied by half kxm square, as I shall repeat down here. So half kx square is equal to E over 2. Why we're allowed to write that? Because we're searching for the position x in which both energies are equal, or another way, each one is equal to half the big boss. But we know that E, one of the forms, is given by half kxm square. So half kx square is equal to half kxm square. We can cancel half k. We're left with x square is equal to half xm square, which means the position at which both energies equate is given by xm over radical 2, which is almost 0.71 the amplitude. Then both energies equate at 1 over radical 2 of the amplitude, which is a non-trivial result. So here, when going from the point O to the point A, initially at this point at the position, the kinetic energy is at its most and the elastic potential energy is 0. As the block starts to move from O to A, US starts to increase and K starts to decrease. There is a point here in which both energies are equal, and this point is perfectly given by x is equal to a over radical 2, which is basically 0.71 a, and that is not equal to the half the amplitude. Alright? And this comes from the fact that functions here aren't linear, however they are quadratic. Conclusion, horizontal oscillator. So I will compare 3 columns related to the state. We will talk about the kinetic energy, elastic potential energy, and the mechanical energy. For any arbitrary position between the equilibrium and the amplitude, we have kinetic, we have elastic potential energies, such that the sum of both gives us the big boss, which is the mechanical energy. At the equilibrium position, the kinetic energy is at max, elastic is 0 because the position is 0, and the mechanical energy, apart that it can be expressed like that, it can be also expressed like that because it's the sum of this and this one. At the amplitude, the kinetic energy is 0, the elastic is at its most, and the mechanical energy would be the sum of this and that, which is given by 0 plus this one, and that would be given by half kxm square. So mechanical energy have 3 different forms given by this, and that. Both energies k and us equate at a position given by 1 over radical to the amplitude. Now, how can we interpret them graphically? Now, in this course, we'll be interested in 2 types of curves. So, first that we have discussed in the previous classes is the variables of motion related or as function of time, in which they represent trigonometric functions. Now here we will be plotting energies, but versus what? Versus position. And this is very important because in the coming slides we will be interested in energy versus time. The mechanical energy E is constant and represented by a horizontal line, so this is the mechanical energy E. The elastic potential energy is quadratic in position, so if you're gonna plot US as function of x, we would expect that this is a parabola up and upward like that. Now, how can we determine the curve of the kinetic energy? So we need to plot now a curve in such a way that the sum of this curve and the kinetic energy should be equal to the big boss, because we're assuming no friction. So this is the equilibrium position. So the kinetic energy should be started from here. As this increase, the kinetic energy should decrease, and because the type of this curve is a parabola, then the kinetic energy also will be parabola going down, such that whenever we consider any vertical slice along these two curves, the sum of this value and the sum of this value should give us the big boss back again. The kinetic energy K, listen carefully, completes the graph US such that the mechanical energy is conserved. K has been plotted in a way such that whenever we consider any vertical slice along the curve, this value plus this value should give us back the mechanical energy. Now we know that US is quadratic, and by default, because this is quadratic, then kinetic energy would be by default quadratic. 3. Periodicity of energies. Consider a horizontal oscillator simple harmonic motion of mass m and stiffness k and thus a period of oscillations. Previously we have seen how does energies vary as function of position. So remember here we have plotted energies as function of position and not as function of time. Always quantities in physics or variables of motion, they can be plotted in terms of different parameters. Now we're gonna plot energies as function of time. Now we're interested in plotting the energy curves as function of time. Consider the position time graph of a harmonic oscillator of period t. So this is modeled by a sine function. So let's recall that these points represents the equilibrium position. These represent the amplitude either up or down in magnitude. And how do we count the period? The period is counted by 4 amplitudes. One way is from the center, choose a point, skip a point, choose another points, and they would be perfectly matching 4 amplitudes, or can be counted from the peaks. So 4 amplitudes. Now this is the position time curve. The period of oscillations of the given harmonic oscillator is t. For the given example, the period of the oscillator is given by 2 seconds. Why? Because if we count from the peaks, so from 0.5 to 2.5, that would be 2 seconds. So for this particular example, the period is given by 2 seconds. Now let's plot the elastic potential energy. Now the elastic potential energy curve is positive and periodic. So let me write here, we know that the position is given by x, which is xm sine omega t plus phi. Let me assume that phi is 0 because it starts from the origin. Now what is the elastic potential energy is given by half k x square. X square would be given by xm square sine square omega t. And we can plot this function as function of time, and we get the following blue curve. Now we need to interpret what's happening. First of all, is this function periodic? Yes, it is. Why? Because it's repeating itself. Here the energy itself, it's not simple harmonic motion. We say that the position or the motion of the oscillator obeys the simple harmonic motion, but regarding the energies we cannot say so. We can only say that the blue curve representing the plot of the elastic potential energy is periodic, because as you can notice, it's repeating itself. Now, good, since we're talking about periodic function, it's repeating itself. What is the period? We can do that by using the same tricks using the same trick from two peaks, and you can notice that from 0.5 to 1.5 the period of the energy is given by 1. Okay, the period of US, so here what do we deduce if you compare both periods? This is the period of the oscillator itself, this is the period of the elastic potential energy. So we can say that the period of the elastic potential energy is half the period of the oscillator, and this is a very important result. Now let's observe the kinetic energy. For similar arguments, if x is given by xm sine omega t, we can find v, and we can determine half mv square and plot it as well. What do we notice? And here, before I refer to the kinetic energy, let me mention something. Now notice that the position of the oscillator occupies positive and negative regions, but because the elastic potential energy half kx square is always positive, we expect that the curve should be always in the positive regime or in the positive region. And notice that half kx square is about position, because we start from the initial position, then both of them starts from the initial position. Now for the kinetic energy plotted in green, the kinetic energy curve is positive and periodic. Now as you can see, also the green occupies the positive region only. It is periodic because it's repeating itself, and if you notice from peak to peak, the period again it's given by 1 second, which means it's half the period of the oscillator. And if you're interested in plotting the mechanical energy again is represented by a horizontal line. And remember, here we're plotting energies as function of time and not as function of position. What is the conclusion? That the elastic potential energy and the kinetic energy are periodic and positive curves. Their period is half the period of the oscillator. And now for the rest of the video, we're gonna solve some exercises on what we have explained so far. An object with mass m is attached to a horizontal ideal spring with a spring constant k. The object is initially at rest at equilibrium where the position x is 0. The object is pulled to the right until the spring is stretched by an amplitude given by a. It is released and allowed to slide across a surface with negligible friction, which means simple harmonic motion. At time t is equal to 0, the object is at equilibrium and moving to the left. The object is stopped and returned to the equilibrium. The block is then pulled to the right to a position of axis 2, double the previous amplitude, and released from rest. Which of the following indicates how the maximum speed obtained by the object changes, and explain why? We know that the maximum speed is given by omega multiplied by the amplitude, which is basically xm. Or we can say that Vm is given by omega multiplied by a. But notice that for the oscillator, we didn't change the mass, we didn't change k, so omega stays the same. Now if I apply the factor of change, because we have set the double of a, so that would be 1 multiplied by 2, so that would be 2. Then we expect that the maximum speed will increase by a factor of 2, so which means the maximum speed doubles, but we need to choose the correct reason, simply because the maximum speed is proportional to the amplitude, making D to be the correct answer. Exercise 2. A mass on a spring of spring constant K oscillates as shown. Which of the following graphs would correctly depict the kinetic energy versus time for the oscillating mass? So this is position. We know that the kinetic energy should be periodic and positive, so it's either, okay, all of them are positive. Now we can start eliminating by considering at the origin the position is 0, which means the kinetic energy should be maximum, so it's either, we can directly eliminate A and we can directly eliminate E. C should be eliminated because energy is periodic. Now notice that the period of the oscillator, because this position is given by T, capital T, then the period of the kinetic energy should be half this period. And if you notice carefully here, so this is a complete period, and if you count from peak to peak, this is half a period, which makes B to be the correct answer. A block of mass m is oscillating horizontally on the end of a spring between the points xmin and xmax, as shown in the figure. There is negligible friction between the surface and the block. The graph of the potential energy U of the spring block system is shown. Which of the following graph best represents the kinetic energy? So if we're searching for the kinetic energy, we know that the mechanical energy would be conserved, By that, the kinetic energy would complete this curve and would be something like that, and it's either A or B, but we need to choose the correct reasoning, and this is because the sum of the kinetic energy and the potential energy must be equal at all points, making B to be the correct answer. Exercise 4. The following graph shows the kinetic energy and potential energy as function of position x for an object attached to an ideal horizontal spring and oscillating on a horizontal surface of negligible friction. Which of the following graphs best represent the object moving in simple harmonic motion from its equilibrium position to its maximum displacement from equilibrium? So they're telling us which graph is correct. They're not asking for a specific graph, they're not asking for K, and they're not asking for U. We can directly eliminate C, E, and D because we know that energies as function of position, they are quadratic and not linear. So it's either A or B. Now, at the equilibrium, we know that the kinetic energy is maximum, so it should be at its max, so this is directly wrong. And B is the correct answer. Why? Because at the position, at the origin, the elastic potential energy, indeed it's 0 because it depends explicitly on x squared. Exercise 5. A group of students are using objects with different masses oscillating on the end of a horizontal ideal spring to determine the spring constant of the spring. The students are varying the mass of the object oscillating on the end of the spring and measuring the period of oscillation. So we're changing the mass. The students then graph the data as the square of the period as function of the mass in order to use the slope of the graph to determine the spring constant, as we have done in previous classes in one of the exercises. One student noticed that they are not keeping the amplitude of the oscillation constant when they start the oscillation. Several students discuss if this will affect their data or not and how to correct the issue of necessity. Which of the following student statements is correct? We know that the period only depends on M and K and they don't depend on the amplitude. So we can directly think about D and E. And why it doesn't depend on amplitude? Because this is simply depends on the nature of the spring, because this is an ideal spring. Now here the other reason is that the oscillations is horizontal and not vertical. In the coming classes we will see that the vertical oscillator is identical to the horizontal oscillator and doesn't depend on the amplitude. So the only reason we can put forward for the period that does not depend on the amplitude, this is only because the spring is ideal. And finally, the last exercise as an exit ticket. A block of mass m is attached to an ideal spring with a spring constant k as shown in the figure. The block is set into oscillatory motion by being pulled back a distance a and released from rest. The block is sliding on a surface of negligible friction. What is the displacement of the block from equilibrium and the elastic potential energy of the spring block system equal to the kinetic energy of the block? We know that both energies equate at a factor of 1 over radical 2 of the amplitude. Okay, so here they're talking about the equality between the kinetic energy and the potential energy, and we have seen throughout the slides that they equate at 1 over radical 2a. Then that's it for me in this video, guys. See you soon in a new one.